Okay, so what's a normal queue? Think what's a good example? A line, right? So if I go to the bank, right, the first one that gets in line, right, is the first one to go to see the teller. Right? Does that make sense? Okay. Yeah. Next person to get in line is the next person, right? So is this a FIFO or a FILO? First in, first out, right? The first one to get into the line is the first one to get out of the line, okay? The other term you'll hear is LI, last in, last out, right? Okay, now unlike a stack is what? First in, last out, or a LIFO, last in, first out. Okay, all right? So this is a normal stack. Okay? Now, this is a slight, this isn't a great example, but so you're at the bank, all right? And in walks Elon Musk. All right? He happens to be the most richest guy on earth. Okay? Does he have to wait in line with us peasants? No, why not? Because he's cool. Okay. Well, you're cool too, so maybe you can do. So what I'm trying to say is there are situations where we want some people to jump the line. There you go. We're like somewhat like an amusement park with fast pass. Okay? Do you get that idea? Okay. In the CS world, this is called a priority queue. Okay? All right. Now, there's a little bit more to this, and that is a priority queue is a queue, except at any time we can retrieve either the maximum or the minimum element that's ever in the queue. Okay? So a similar situation to the bank would be the person that gets exits the queue next is the one with the most amount of money. Okay? So a whole bunch of people go into the bank, all right, and the teller says, well, the person with the most amount of money come up next, you're going to come next, all right? So what does everybody do have to do in line to figure out who has the max amount of money? Well, they have to figure out who has the most money. Does that make sense? Okay, all right. Now that's a very contrived example. In CS, Dijkstra's algorithm. All right, everybody heard of Dijkstra's algorithm? Many of you have used this algorithm because you drove here in a car, all right? The algorithm that gets used for Google Maps and Apple Maps and any path planning is a variation off of Dijkstra's algorithm, okay? Dijkstra's algorithm does path finding between any 2 points on a graph, and it finds the minimum distance, okay? All right? In that algorithm, you have to choose the least expensive path or road to go on next. Okay, so if you think about it, like if I am here in University of Indianapolis, right? If I want to go home, which ways can I go? I can either go west on National, I can go east on National, right? So I really have two different options. Okay, all right, so let's just imagine I go west on National, okay? Now which way can I go? I can go south or north on whatever that road is. Oh, I can go straight through that intersection, okay? Or I also could come back here and go east, right? So you see now I really have 4 different options. I can either do east on National or those 3 other intersections. Okay, does that make sense? Okay, so inside the Dijkstra's algorithm, it's constantly computing which of these paths I should actually choose to go on. And that's generally how path planning works, okay? So in Dijkstra's, we need to always know what is the least cost element that was added to, we're going to call it a queue. It's not really a queue, but it is a queue that can always ask what is the least valued element in this queue. Okay, does that make sense? Okay, all right. So that's especially a priority queue. Now just to motivate this, before you know how all the internals work, so like imagine that you didn't do Zybooks, could I do this with a list? All right, so let's just say the values 5, 2, 1, 6, 8, okay, were inserted into this data structure. and I always want to get the minimum element out. Okay? All right, so what's the minimum element there? 1, okay. What was the big O, or cost, for you to find that element? Yeah, it's O of n. Okay, so find min is O of 1 for this situation right here. Okay, all right? What about inserting something? If a new number comes along and I want to insert it. Why? How about we just say we have an ability to put it on the end. Another way to think about this is a linked list. Okay, so I could put an O of 1. So insertion, either or of n if I really want to shift it. I could just always put it on the end. Let's just say that's that's O of n. I'm sorry, that's O of n. Let's just say insertion is O of 1. Okay, could be n. Okay, but O of 1. Okay, can anybody think of a better way to do this without what you learned in this chapter? Notice I'm just putting new elements on the end. Okay? And I'm always asking for the minimum element. Could I insert in sorted order? Right? Could I do that? Would that help finding them in? Right? So like number 5 comes along. Excellent. Okay, all right, 5. I insert a number 2 into this list. Oh, 2 is less than 5. A 1 comes along, put that there. A 6, oh, that will go there. An 8 will go there. Okay, so now what is the find min time? Yeah, now this is O of 1, right? But what is insertion? So how fast can I put an element in here and shift up the rest? Yeah, O of n. Right, O of n. Okay, all right. Now, this insertion does depend on the values that we're inserting, right? Technically, I think I could store this backwards, and if the elements that you insert are always small, then they're always go on the end. But in general, this is what we'd have, right? So we have an n, we have an n. That's not great. Okay, all right? Okay, so anybody know what in Zybooks are we talking about in this chapter? How does this one work? No idea. All right. What about a binary search tree? Could I insert it into the binary search tree? Okay, so let's do it. Let's make a 5. Okay, now I insert a 2. 2 is going to live over there. Okay, and then I insert a 1. 1's going to be over there. Okay, and then I insert a 6. And then I insert an 8. Okay, all right, so what is insertion now? How expensive is it to insert something in a binary search tree? No, it's not 1. It's not 1. It's not 1. Does this at all depend on the size of the tree? If you say yes to that question, it's not O of 1. Huh? It's log n, right? Because I, on average, have to go the height of the tree. So that's O of log n. Okay. What about find min? It's also log of n, but we have a slight problem. So finding the smallest element in a binary search tree, by the way, what's the algorithm for it? Did we cover this? The new book splits trees up. There's a chapter towards the end of the book that goes into more details about trees. Where's the smallest element in the tree? Far left-hand side, right? So if I'm on my route, if I just go left, 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 I will find the smallest element. Okay, all right? So like, for example, if I had like 1.5, it would go there. What's the smallest element? Left, 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 1. Okay, what about the maximum element? Right, 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 right. Right, okay, all right? So finding the smallest element is log n. Okay? Now, the problem is I also have to remove that element. Oh shoot, did we completely forget about how deleting things in binary search trees? We did, didn't we? Was that in Bazai books? Shoot. All right, well, you guys get to tell me how to do it. How do you delete, how do you delete something in a binary search tree? Okay, all right, so we have the leaf situation. I'll just do the deletion and a BS2. A later homework assignment has you implement this. So, all right, so what sort of situations are there? One is a leaf. Okay, somewhat. There's three different options. Here, I'm going to draw you a binary search tree. All right, somebody give me random numbers from like 0 to 50. I'll just make a binary search tree. 7, good. That's a bad one. 50. We're going to do 20 first, and then we're going to do 7. Okay. 48. Okay, what did you say? 45. Okay, 45 goes over here. 14 is less than 20 but bigger than 17. Sorry, 7. So 14 lives over there. 2. 2 is smaller than 7. 50. Let's do 2 more numbers. 3. 3 goes over here. Since you have 45 on there, how old are you guys? 19? 19. That's less than half my age. It's so sad. It's so sad. Somebody bring me my cane. All right, is that an okay tree? Did I make any mistakes? Yeah, I think that's right. Okay, so given this tree, there's no 2-year-olds in here, so I'm happy about that. And there's no 50-year-olds. So which node would be deleting if it's a leaf? Wait, what? Oh, 3, 19, 45, and 50. 19. That's a 19. Okay, all right. So what do I do if I want to delete a leaf? You just get rid of it, right? Okay. Now, the tricky part, and one of the reasons why we haven't covered it so far, is implementing this is really tricky. Because you have to find the element that you want to delete. And then what node actually has to get changed if you want to delete this? The parent. Okay? So normally with our binary search tree, each node has a left and right pointer. Okay? Except if you want to delete stuff, either you have to be really smart in the way that you traverse the tree, or you have a parent pointer. Which isn't the end of the world, but then it uses more memory. Okay? All right? So yes, all right. So we have to change the 2 so the 2 doesn't have a child. Okay? All right? So that is easy. So 3, 19, 45, and 50. Okay. What's another situation that I might want to delete? The root? No, we don't delete the root. No, that's the hard one. No, that's no. 2 and 14 would be easy. Yeah, so the one child nodes. Okay, so that would be deleting that 2 would actually be easy, and deleting this 14 would be easy. All right, so how do you do it? I mean, you can think about flipping, right? But the left child of 7 becomes 3. That make sense? Okay, all right. The right child of 7 becomes 19. Does that make sense? Okay, so maybe like, I should have like words here. But leaf is just delete it. This is promote your child to be yourself, is maybe one way to think about it. Okay, so the 3 would go right here. Does this violate the binary search tree problem though? If the 3 is right here? doesn't, because 3 is less than 7 because it's over here on this left-hand side. Okay, all right, so this isn't so hard, is one-child nodes. The problem comes in if you have two children nodes. Okay, and this would be, let's see, if I try to delete a 7, 48, or 20. That would be deleting two children nodes. Okay, all right. Anybody know how you do this? Can we come up with an idea? Okay, let's make this easy. Let's remove the 20, the root node. I think you all lied. This should have been in Zybooks. Okay, so 19 can become the root, or what other number could become the root? 45 can also be the root. All right, so what rule did you follow for each of those?
It has to be less than 48.
Yeah, less than 48. I mean, if I had another, if I had 47 over there, 47 is less than 48. But that you can't use that one.
It has to be, well, it has to be the smallest number on the right side.
Yes, it has to be the smallest number on the right side, or the largest number on the left side. Do you get that? Okay, all right. So deleting the 20 is inherently recursive, because I can't just remove that and fix its parent, right? I have to find the smallest element, or the biggest, let's just go the smallest element over on the right-hand side and delete that and put the 45 up top. Does everybody get that? Okay, all right, so 45 is a leaf node. Well, that's rather convenient, all right? That's easy to kill. Now, if this one, 45, had a child, it's harder to, this is sounding mean. It's harder to kill a parent with a child than it is a leaf. Okay, anyway. All right, okay, so now deleting that 45 is hard. Deleting the 45, the 47 has to get promoted, and the 45 can go to the top, so it's inherently recursive. Does everybody sort of get that? Okay, all right. Anybody want to take a guess what the big O of deleting a value is? This is why we did all of this. All right, deleting a leaf. Okay, so log n. So what is the time to find the element that you want to delete? Log n, okay? And then I just get rid of it. That's a piece of cake. All right. Removing a node that only has one child, like 2. Log n to find it, and then fix the pointer, right? So that's log n. All right, what about 2 children nodes? Like deleting the 20. Yeah, it's also log n. Because worst case scenario is I just have to traverse down to the height of the tree to start moving nodes up. Does that make sense? All right. So deleting a node in a binary search tree is log n time. Okay. All right. So let's bring us back here. So if I did this in a binary search tree, all of them, insertion is log n, and finding and removing the minimum is also log n. Okay? Now, there's one little devil in the detail problem. These speeds depends on the numbers, right? If I insert the values into a binary search tree in a bad order, it would be not log n anymore. What would be a bad order? What? Yeah, O of n. So if I inserted values that were sorted already, I no longer have this nice structure happening. It becomes a linked list. All right? And then all of these log n turns into n's and it slows down. Okay? Now again, later on in the semester, we'll talk about how we can rebalance those trees, which is a little bit better. Okay? And another thing that sort of hurts this is this requires extra memory. Okay? All right? Now, in this scenario, when I have a list, I can think of that as an array. So this is 100% space efficient. Right? Inserting into a sorted order, I don't have any pointers whatsoever. So that one's 100% space efficient. Okay? What about a binary search tree? Nope. Come on. How space efficient is a binary search tree? Right, so we have a value, and then we have a pointer and a pointer for every single node. Okay, all right, so I'm just gonna, it depends how much space the value takes up, but let's just say 33% space efficient. All right, so that is like a value is the same size as a pointer, and I've got a value and 2 pointers, so therefore I'm using 3 equivalent memory locations to only store 1 piece of information, so that's, not so great, 33%, okay? What if I told you there's a way that we can make this log of n? You ready for this? Does anyone want to tell us how a heap works? No. Okay. So remember this binary search tree? What's the rule if I try to insert something? Sorry, what was that? Yeah, so if it's greater than, it's on the right. If it's less than or equal to could be either side, it's on the left-hand side. Okay, you got that? Okay, all right. So the idea here with a heap is we are going to use a completely different rule. Okay, and let's use, do you want to go small or big? A min heap or a max heap? Max. Okay, so a max heap, all right, has a completely different rule, and this rule is the parent is always larger or equal to both children. Okay? That's the rule. There's nothing there about lefts and rights. Okay? All right? Okay. So let me draw you a max heap with these numbers, right? So which value has to be the root then? Huh? Max. The parent is always larger. That says larger. The 8, right? Okay. The 8 has to be up top. Okay. And now what nodes could be its 2 children? Yeah, technically could be any of them. But if I put the 1 and the 2 there, I've got a problem because I have to put the 5 and the 6 someplace. Okay, all right? So let's do a 5 and a 6. Okay, and then I just have the 1 and the 2. And let me put the 1 there and the 2 there. Okay, and let me put little things. There we go. Okay, all right? So this is a heap. Okay? There is no relationship between the left child and the right child. The only restriction is the parent is greater than either of its children. You got that? Okay? Okay. So, let me, now, we were just looking at the numbers. Now, let me insert a new value, okay? And let's see, somebody say a value between, I don't know, 0 and 30, and I'll put it in here. 17. All right, so here's what I'm going to do. I am going to put the 17 right there. Okay? Now, did that violate my heap property? Yes. So guess what we do? We fix it. And then we flip them. Okay? So the 6 and the 17 are in violation, so I flip them. And I apologize because this is pen, but we're going to do it anyway. So the 6 goes there, 17 goes right there. Okay? Is there a violation of my heap property? Yes, between the 8 and the 17. So I flip them. Okay? So now, is my heap property violated? Shouldn't be, no. Okay? Did I ever have to change anything over here on this left subtree? Okay? Would I ever have to? Why not? Yeah, because if this was valid before, and this got even bigger, well, all of those numbers must be smaller than the thing before, so therefore it's going to stay the same. Okay? All right, so, $1 million question. What's the big O, and by the way, this is called a bubble up operation. What's the big O of inserting into this heap with a bubble up operation? How many flips did we do? Flip, flip. The height of the tree. Log of n, yeah. That's the big O of log of n. Okay? All right? And I will say it is big O of log of n no matter what order of values you put in there. Okay? All right? Okay. What's another number you want me to put in? Four. All right. Any guesses where I'm going to put the 4? Far right, yep. Okay. Why am I doing it like that? Because I filled the tree up perfectly. Okay, all right? So this is what we call a complete tree. And where's the next node going to go? Over there, right? So then I'm going to fill it up like this. Okay, now if I fill it up like this, I keep that binary thing essentially maximized at all times. Okay, all right? So the 4, am I violating my heap property? I look at my 4 and my 8 and I don't, so I'm set. Okay, so I checked and I didn't have to do bubbles up. Okay, are we good with this? Is everybody good with this idea? Okay, so the bubble up operation, I just flip them, okay, until I don't have to flip them anymore. Okay, all right, and I'm guaranteed that that's going to be log n because the height of this tree is going to be the log n of all of the nodes in here because it's the height. Are we good with that? Yeah, this is not so clear because it's in pen. All right, what about removing, right? So finding the maximum element, so insertion is log n, find max, what's the big O of that? This is easy. 1, yeah, this is easy. It's O of 1 because it's at the root. Well, that's a piece of cake, all right? Now, what about deleting the max? So I want to get rid of the 17. Remember how we bubbled up? Yeah, we bubbled down. Okay, now which node, the 5 or the 8, could go up top? The 8, okay? Not the 5, right? If the 5 came up here, 5 is smaller than the 8, and that would violate the heap property. Okay, all right? So what we're going to do is we are going to get rid of the 17. Yeah, get rid of the 17. Actually, there's one more thing that we do. Get rid of the 17, and then what do we put in its place? Remember from Zybooks? No. What was that? I put the 4 there. Okay? All right? And watch what happens. I put the 4 there. Okay? So the 4 is now going to be up top. Okay? And now I clearly violate the heap property. Okay? And now I do a bubble down and I swap it with the larger of the 2 children. So the 8 comes there and the 4 is in that spot. Okay? And now am I violated my heap property? I have a 4 and a 6. That's wrong. So the 6 goes here and the 4 goes right there. Okay? Anybody want to take a wild guess on why I took the 4 out? What? Not really. No. It's the last spot that got inserted. Okay? Because now when I insert something, it's going to go into that spot right here. You got that? Okay? Now, had I just chosen the maximum, it could have been way over here. And then I have sort of a blank spot that's not complete on that bottom row. I've got an empty spot and then other stuff over here. And then I have to remember, oh yeah, go fill in that spot before anything else. Okay? So that's why we choose the last element, all right, to move up to the very top. All right? And then we sort of do a bubble down, which sort of figures out where it goes. Okay? Are we good with this? Yeah? Okay. Do you want me to take it to the next step? So, oh, by the way, what is the deletion? Big O of what? Yeah, this is log n as well. Okay? Again, Because the worst situation is I have to bubble all the way back down, and the height of the tree is log n, and that's going to take a log n time. Okay? Okay. All right, since it's 2:37, and you guys seem like you're picking this up pretty quickly, let's do an in-class activity, and then I don't have to take attendance. And what we're going to do is I'm going to give you some numbers, and we're going to see if we can draw trees. If you have a piece of paper, okay, so what numbers do you want to insert? What are some random numbers? 7. Another random number. 24. 12. Let's go from 0 to 100. 76. 3. 4. And 1. Okay? So what I want you to do, 1, 2, 3, 4, 5, 6, 7. Oh, that's perfect. Let's do one more. Let's do one more. 94. Okay? Build a max heap from these numbers. Okay? Now, if we all follow the same rules, all of our heaps should look exactly the same. Okay? If you look at the numbers and go, ooh, I know what should be up top, I know what should be on the second row, it's not going to look the same. Okay? This should take you a little bit of time. So if you only have one tree on your piece of paper, it might be wrong. Are you ready? Is everybody still ready? We ready? Okay, all right. How do I insert a 7? I just do nothing, so that's a 7. Okay, 24, where does it go? What? Right, it goes below first, and then I swap it. Okay, so let me actually just do it this way. I'm going to sort of draw different versions of the tree as it went on. Okay, all right? So if I add the 24 below it, I get a 24 and then a 7. Okay, all right? Now where does the 12 go? 12 goes right here. Okay? Remember, I'm taking a number and I don't have to look at it. I know exactly what spot it's going to go next. So the 12 goes right there. So 24, 7, and then 12. Okay? All right, where does the 76 go? What? No. Bottom left. Bottom left. And in a second, tomorrow, I will show you why this is super important. All right, so I have 24. I'm just going to copy everything down. 12, 7, 76. And then what happens? Yeah, flips up. So that becomes a 76. And that becomes a 7. All right, 76 and 24. 76 and 24. We good with that? Okay, all right. Next number is a 3. Where does that one go? The next spot, which is right here. Okay, and that actually keeps the property because I have 24 as being the parent, and then 3 is right there. So let me just copy this down. 24, the 3 is right there, and then the 7 goes right there. Okay? All right, where does the 4 go? Right, the next spot, which is to the left of the 12. Okay, where does the 1 go? Right here, far right, good, yep, 76, 12, 1, 4, 24, 3, 7, all right, and 94. Far left, right, all the way over here, okay? Is everybody understanding what's going on now? Right? And now I violate that property. Oh, sorry. I violate that property, and now I flip, 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 and it becomes the top one. Okay? So now my root element is going to be 94, and then I have 12, 1, 4. That was 94. Sorry. 76. 7. No. 76, and then a 3 is over here, and then a 24. No, I messed something else up. Oh, and then a 7. And then a 7. Oh, sorry, there we go. Okay? All right, we good with that? Did everybody get that exact same thing? Really? Okay. All right, so anybody want to take a guess why we add in a specific spot? Anybody want to call me out on a statement I made about 15 minutes ago? Is this any more space efficient than my binary search tree? No. All right, and I'm going to not tell you why. And I'll tell you tomorrow, Wednesday in class. Or you can look inside books. Okay? It turns out we can store this in 100% space efficiency. Yay! All right. All right. Questions on this? So this is insertion. Oh, I guess we didn't delete anything. You want to delete something before we leave? Let's delete the 94. And by the way, we only delete the root. What happens if I delete the 94?
You get 2 truths from the branches?
No, there was a step before that. Yeah, promote the 7. right? Which is the last one to go to the top, okay? So here, I'll just redraw this like this. 76 and 12 and 1 and 4 and then 3 and then 24, okay? All right, so I just promoted the 7 up to the very top, and now what do I do? Yeah, bubble down, right? I'm going to look for the largest of the two children, which is a 76. So I'm going to, oh, look at that. Swap them. All right, so I got the 76 and the 7. And now what do? But keep bubbling down. 7 is smaller than the 24. Well, 24 and 3, 24 is the bigger one. So the 7 goes right there, and then the 24 is right there. Okay? And that is log n time again, because I'm maximally going to the bottom of the tree, and because we are filling it in a certain way, I'm guaranteed that it's log n time. We good with that? All right, so this is a heap, okay? And then on Wednesday, I will show you how we store this with 100% space efficiency. All right, so make sure your name is at the top, and this will be attendance and an in-class activity for the day.